Hey guys, give me a second to pull my iPad up, and then we'll get started. It is now 7 o'clock and 30 seconds. Okay, sweet. Now we've got an iPad and review. That's not for you. I was not late, Savian. I was literally right on time. Not at all late. But I'm glad you're here. I see Lindy. I see Savian. Who else is here? The app I use for demonstrating on my iPad is called Explain Everything, Lindy. And if you are interested in doing math on an iPad in front of students, it is the best, for sure. Just Saving and Lindy, huh? According to my end, it says there are 4 people watching, but maybe it's just the 2 of you. Oh, Xander's there. Cool. So my thought was to go through the core standards for uh, quarter 3 and quarter 4, based on the test that I've already given. So I was thinking of going through the core standards quarter 3 tests that I gave pretty recently, and then the snapshot on sequences, which would kind of be the best introduction to the quarter 4 standards that you guys have seen so far. But for the 3 people there, oh, now that we've got 2 more, who else is here besides Lindy, Savian, and Xander? Yes, Xander, that is my parents' dog that we were dog sitting, and my parents are just picking up right now. Correct. That was a dog. Cool. So I'm going to bring up. I haven't heard who else is here, so hopefully it's worthwhile to go over the core standards. If it's only Xander, Savian, and Lindy, then it's not all that worthwhile to go over core standards. But I will anyway. I guess other people will watch later. Yeah, it's in my car. My keys are in the Adeline. Oh, good. Lorenzo's here too. Okay, so it is now 7:05, and I'm actually going to start reviewing. Oh, and Nancy's here. But I think all of you have met these standards. But hopefully other people will watch later, and this will be useful to them. So this is the test 3 that people who had not already met the core standards did for units 5, 6, and 7. Unit 5 was on functions and function composition and transformations of functions. Unit 6 was on exponential and logarithmic functions, and it corresponded to chapter 5 in the book. And then Unit 7 was on polynomial or rational functions, which corresponded to chapter 4 in the book. And Unit 5 kind of corresponded to like chapters 1 and 2 and 3, really, all together. So here it is. Let's go. Give an example of a relation between two real-life sets that is a function. Explain why the relation is a function. So a possible example of a relationship which is a functional relationship is perhaps the function that takes inputs of people and outputs their fathers. Everybody has, well, let's do mothers. Everyone has one and only one mother. So function name is M for mom. Inputs are people, and the outputs birth mother. Everyone has exactly one birth mother. So the definition of a function is that every input has exactly one output. So every person has exactly one birth mother. And then give an example of a relation between two real-life sets that is not a function. Explain why the relation is not a function. So Lorenzo just said he doesn't have a dad. We could use that one, but I don't want to make fun of him because I do that enough already. So let's say we'll just invert our function m, which will not be a function. So function c for child has inputs. Oh, whoops. A relation, which is not a function. Not a function c. Relation C takes inputs of people and outputs their child. So here, to explain why the relation is a function, we would say that every person has exactly one birth mother. But down here, we would say many people have more than one child. Inputs would have multiple outputs. Cool. There we go. That was an example of a relation in real life that was a function. Every person has exactly one birth mother. And then a second example of a relationship from real life that is not functional. Many people have more than one child. Okay. Any questions on number 1 from this test? All right. Number 2. There was a function root x and another function x minus 5. And the question asked you to graph f composed with g of x and g composed with f of x. So let's see. I'm going to make a y-axis and an x-axis. And then we're going to say, I'm going to start, you didn't have to do this, but I'm going to start by graphing root x. So square root of 1 is 1, square root of 4 is 2. That looks like the square root of x. So here's f of x equals root x. And then now it tells me to graph f composed with g of x. So that means I have to take the g of x function, x minus 5, and plug that into the f function. So when I make f composed with g of x, I should make the square root of x minus 5, which is a translation of the x minus 5 graph, 5 units to the right. So let's make a copy and send that graph 1, 2, 3, 4, 5 units to the right, so that there is f composed with g of x equals root of x minus 5. And then they ask us to do g composed with f of x, which means I'll take the f of x function and plug it in to g of x, which will be root x minus 5. Root x minus 5, which is a transformation of my original f of x function down 5. So I'm going to duplicate and go 1 space, 2 space, 3 spaces, 4 spaces, 5 spaces, down 5 to have made g composed with f of x, which is root x minus 5. Cool. And then it says, explain why the minus 5 in g of x moves the graph of f in either a positive or negative direction, depending on the order of the composition. So we can see here on the next part what you had to do to get a 4, that in f composed with g of x, inputs 5 greater than the inputs to f of x yield the same outputs as f of x. In g composed with f of x, the same inputs as f of x yield outputs 5 less than the outputs of f of x. So here we had a graph going. Oh, did I do this wrong? I did the whole thing wrong. X minus 5 should have gone right 5. That's the problem. Crucial issue. This whole thing should have been 1, 2, 3, 4, 5, which makes my graph a little bit in the way here. So let's see, can I grab just that? Ooh, I can. Nice. So let's put that label there, and then this label 1, 2, 3, 4, 5. There we go. I wrote about it correctly, but I didn't graph it correctly. Root x minus 5 was 5 to the right. And get that label there. Or how about, that looks good. 5 down, 5 to the right, original. Cool. 5 greater than the inputs to f of x yield the same outputs. So using the inputs that are 5 larger over here, give me the exact same outputs. The y values have not changed. And then in G composed with f, the same inputs as f of x, all the x values are the same, yield outputs that are 5 less. So all the outputs, the y values are 5 less than the outputs in the original function f of x. Whew, cool. Any questions on number 2 from this test? Cool. Seeing none, let's check out the next one. Number 3. So I'm still looking at a Unit 5 question. This was a core standard from Unit 5. Below is the graph of h of x equals the square root of 1 minus x squared. Sketch and label the graphs of h of 2x and negative 2 h of x. So h of 2x, which is that right there, should be a compression. And it's a horizontal compression, so the center is the y-axis, by 2. So h of 2x I'm going to do in blue, and let's see, I was at negative 1, so I should be at negative 1/2, and positive 1/2, and nothing happens there, so I'm like that, and I'm like that. Good. So I have compressed the graph. If I plugged in 1/2 there and times it by 2, I would get 1. H of 1 should be 0. So h of 2 times 1/2 gives me 0. Cool. Then negative 2 h of x should be a stretch. So stretch vertically by 2 and reflect in x-axis. So, by the way, if we were thinking transformationally, which is better, we would call this dilate about y-axis by 1/2, and we would call this dilate about x-axis by 2. The book uses the language of stretch and compress. I prefer the language of dilate, but either one is fine. And let's see, I'm going to do that negative 2 h of x in purple. Purple. So here we go. We're going to come down to there like that-ish. That was kind of ugly. Let's see. Do a little bit better. Oh, that's better. And much better. Okay. There it is, the graph of h of 2x and negative 2 h of x. It said label. So here's h of 2x. This was the original h of x. And this is negative 2 h of x. Okay. This was another Unit 5 core standard for the course. Any questions on that one? Seeing none, I'm going to move on to number 4. Cool. So now I'm looking at a Unit 6 standard on exponential functions, and one of the core standards on exponential functions was that you are able to find inverse functions. So let's find an inverse function. The strategy I like is to switch to just an input variable and an output variable. I think in my notes I told you to use b equals 3 times a, 3 times e to the a minus 2. And then we're going to solve this for a. So let's see, start by dividing by 3. Cancel, cancel. Now I've got b over 3 equals e to the a minus 2. And I'm going to rewrite as a logarithm. So now I've got a minus 2 equals the natural log of b over 3. And then I'm going to use plus 2, plus 2, plus 2. And a equals the natural log of b over 3 plus 2, which means that the inverse function, j inverse of x, is equal to ln of x over 3 plus 2. Cool. Notice that the minus 2 here became a plus 2 here. Oh, but I lost the plus 1 from the very beginning. Shoot. I'm making all kinds of mistakes today. Plus 1. So then this is going to have to be a ln. Okay, so I had b over 3 minus 1 there, and then minus 1 there, and then b over 3 minus 1. And let me just do the whole thing over because I made this mistake. My bad, everybody. I didn't see that minus 1 in the problem. Okay. So the original function should have said b equals 3e to the x minus 2 plus 1. Okay, so my first step needs to be minus 1, which means that b minus 1 needs to equal 3e to the x minus 2, which I can now undo the 3 and get b minus 1 over 3 equals e to the x minus 2. And now I can rewrite as a log. And I like to rewrite it with a input variable a. Better. So now I can get a minus 2 equals the natural log of b minus 1 over 3. Looking better. And then when I add 2 to both sides, plus 2 plus 2, now I'm at a equals the natural log of b minus 1 over 3 plus 2, which means that j inverse of x equals the natural log of x minus 1 over 3 plus 2. Okay, that's it. And as I was pointing out earlier when I caught my mistake, this plus 1 has become a minus 1. This minus 2 has become a plus 2, and this times by 3 has become a divide by 3. It used to be that the last thing that happened was a plus 1. Now that first thing that happens is a minus 1. It used to be that the next to last thing that happened was a times by 3. Here it's divide by 3. It used to be that the very first thing that happened to x was minus 2. Now the very last thing that happens to the x is plus 2. That's what should occur in an inverse function. Any questions on number 4? Okie doke. Number 5. So I'm going to need a calculator. I'm going to use Desmos because that's the one I have on my iPad, but you could do this part with any scientific calculator. Doesn't need to be Desmos. Okay. And the first thing that it's saying is we're again letting j of x equal 3e to the x minus, x minus 2. And plus 1. And then I'm going to name the inverse function h of x. And we remember from the last problem that it was the natural log of x minus 1 over 3 plus 2. Cool. So those are my two functions. And the first thing they want me to find out is j of 3. So since I have Desmos, I can just plug in j of 3. But if I didn't have Desmos, I would just do 3 times e to the 3 minus 2 plus 1. And it is going to be, either way you look at it, 9.15. J of 3 equals 9.15. Okay? And then now we have to find x such that the inverse function equals 3. So I'm going to call this number, j of 3, let's call it a constant c that we're going to get to use later. And it's asking me, how could you make the inverse function give an output of 3? Well, if I know that the original function has an input of 3 and I get 9.15, then the inverse function, when I plug in h of the number that gave me 3 in the original function, I should get an output of 3 in the inverse function. So the same answer is true, 9.15. Then it asks me to find a number such that j of x equals 12. So I'm solving. So if 12 equals 3e to the x minus 2 plus 1, I could solve for the value of x that works here, or I can just evaluate the inverse function for what happens when you plug 12 into the inverse function. So I can go back in here and I can say, what happens when in my inverse function I plug 12 in? So my inverse function says ln of x, which is going to be 12 minus 1 over 3 plus 2. It's going to be 3.3. X equals 3.3. And if I save this as a constant, that I need to use again. Then when I come in here and find J inverse of 12, it'll be the exact same thing, 3.3. And then to score well, you had to be able to explain what you did. And Claudia, welcome. We are going over this test, which is test 3 on units 5, 6, and 7. Kind of covered all of the material that I meant to cover in the third quarter. And I'm on number 5, looking at a core standard from unit 6 on exponential functions. And the core standard is to understand the inverse relationship between exponents and logarithms and use this relationship to solve problems involving logarithms and exponents. And here we are realizing that for any input C, J of C equals, how about D, and J inverse of D equals C. So the answers to A and B must be the same, as well as C and D. Cool. Any questions on number 5? Understanding the inverse relationship between exponents and logarithms. Oh, we're up to 11 people. Some more people have gotten here but haven't said hi yet. Oh, Hazel's here. Well, Hazel, that's a good question. I'm glad you asked that. If you kind of understood it, the whole problem, you might have realized that this had to be equivalent to this, which is how I did it. And you would have said, oh, since I know these are the same, I'm just going to do that once because that's easy. I already know the inverse function. I found it on the last problem. And since I can just plug in, but what's Uriel doing here? Uriel geometry is tomorrow. This is pre-calculus. You know that, right? Hopefully. Anyway, Hazel's question was, how do you do C? So I realized that C was the same as D, so I just put 12 into the inverse function and got 3.3. But if you perhaps had not realized that, because for whatever reason, you would have solved the equation, let 12 equal 3 times e to the x minus 2 plus 1, and thank you, Lindy. Uriel, you're welcome to stay and go over pre-calculus. And then you would say minus 1, minus 1. So that 11 equals 3e to the x minus 2. And then divide by 3 and divide by 3. So that 11 thirds equals e to the x minus 2. And then rewrite as a logarithm so that the x minus 2 would equal the natural log of 11 thirds, and then add 2, so that x equals the natural log of 11 thirds plus 2, which you then would have needed to plug into a calculator of some sort, be it scientific or otherwise. The one I have here on my iPad is Desmos, so I would have had to check out what is the natural log of 11 thirds minus 2, plus 2, and it is 3.3, which I then get again when I do the exact same thing in evaluating J inverse of 12. Hazel, did I answer your question? Cool. Excellent. I'm getting some requests. Can we review extended standards for quarter 3 and 4? Davian says, yeah, do extended. Okay, so I think I've got number 6 and number 7 and number 8. So I have here graphing the function and the inverse, and then a polynomial function and a rational function. I think I'll go ahead and do those because I know that all of you guys here that are watching, a lot of you need extended, but I want to make sure that the core standards questions are answered first, and then I can start working on extended. But as soon as I'm done with the third quarter extended, I'm happy to go over as soon as I'm done with the third quarter core, I'm happy to go over third quarter extended. So on number 6, I'm now looking at another Unit 6 core standard, graph exponential and logarithmic functions showing intercepts and end behavior. And I'm plotting 3e to the x minus 2 plus 1, which is my j of x function. I'm going to make a little xy table. I'm going to say, let's see, we already know a couple points that we got, that when we plug in 3, we get 9.15. 3 gives 9.15. And then we already got that when we plug in 3.3, we get 12. So 3.3 gives 12. So 1, 2, 3. We got 9.15. There it is. Let's do this in blue. And then already out by 12. So it's got to be going up this way like that. If I plug in 0, I get, or let's plug in 2, gives me, well, if I plug in, 2 minus 2 is 0, e to the 0 is 1, 1 times 3 is 3, plus 1 is 4. So I'm plugging in here 2 to get 4. 2, 4 gives me that point there. And then let's try a point at 0. I'm going to have, with just any old scientific calculator, I could plug in 0. So obviously with this calculator, I can make a chart. 0 gives me 1.4. So here's 0, 1.4. Okay, and I happen to know that this function has a horizontal asymptote at +1 because I can see this +1 right here. So I'm going to sketch in that horizontal asymptote. And now I'm pretty close to the horizontal asymptote with this value. So I'm going to go ahead and lay in the graph, which goes like this and then up like that. Great. So there's j of x. And then I'm also supposed to graph the inverse function. Well, the inverse function needs to have a vertical asymptote. And I can plot all of the values just inversed. So I can say 9.15 will give me 3. 9.15 gives me 1, 2, 3. And I'm not going to plot 12, but 4 gives me 2. 1, 2, 3, 4 gives 2. And 1.4 gives me 0. So 1.4 like that gives me 0. So the inverse function must look like that. So there's j inverse of x. State the asymptotes, domain, and range of both functions. So here's an asymptote at x equals, y equals 1. And here's another asymptote at x equals 1. State the asymptote's domain. The domain of this function is the set of all reals, such that x is an element of the real numbers, like that. And then the range is the set of numbers y, such that y is greater than 1. And then down here, we've got a domain, which is the set of numbers x, such that x is greater than 1. And then a range, which is the set of numbers y, such that y is an element of the reals. Sabian, I think sorry, Hazel, if you didn't state the domain and range, I think you wouldn't have gotten a 4, was how I scored it. If you graphed it correctly, you got a 3. And then Sabian was asking a Desmos question about getting tables. So I think if I return, so here I was looking at this function j of x, which was in its functional form, and I hit the little gear button, which gives me like settings, and then I hit the little table button next to j of x. So I'm looking at j of x, and now I'm grabbing the little table, and the table spits out a table for j of x values. Hopefully I've answered Savian's question, and then Olivia has a question. So Savian, I'm putting away Desmos. And Olivia's question is, how did I get the range for j of x? So the range was y value is greater than 1. Well, I know about exponential functions that 3e to the x minus 2, as I raise e to very negative values, like negative 1,000, that's going to be 1 over e to the 1,000th, which is like just a minusculely small number, very close to 0, like 1 e to the 1,000th. So 1, a millionth. So this is, if I plugged in negative 100, I'd be looking at 1 plus 3 millionths. So obviously, as negative numbers are plugged in for x, this function is going to get closer and closer to 1, because I get a very small value close to 0 and then add 1 to it. So this function is getting closer and closer and closer to just 1, which is what we mean by asymptote at y equals 1. So all of the outputs are greater than 1. They get closer and closer to 1, but they never reach it. So I'm saying that the range is the set of y values such that y is greater than 1, but never equal to 1. And of course, it goes up forever. So all of these y values greater than 1 are a part of the function, a part of the set of outputs of the function. So, Olivia, I could have just analyzed this and seen that +1 and been like, bam, that +1 is going to be the one right here in the range. Or maybe I looked at the graph and I'm looking in and seeing, oh, it never gets lower than 1. The range must be greater than 1. Cool. Those were great questions about number 6. Any further questions about number 6? These sessions are so much better when the people who actually have the questions are asking them. I love it. Number 7, sketch a graph of the polynomial function p of x equals negative 2x to the fourth plus 8x cubed minus 6x squared. Your graph should show whether the function is positive or negative, the zeros, and the end behavior of the function. Cool. So it looks like we ought to do some factoring. So right now I'm seeing negative 2x to the fourth plus 8x cubed minus 6x squared. I'm going to factor out, looks like a 2x squared, which leaves me with, I'm going to factor out a negative 2x squared. So I'm now at x squared and then minus 4x and then plus 3. And I can factor x squared minus 4x plus 3. Looks like it's going to be a minus 3 and a minus 1. So now I'm at negative 2x squared, x minus 3, x minus 1. Cool. So I can plot my zeros of the function. Looks like I've got a 0 at 0. I've got a 0 at 1, 2, 3. And I've got a 0 at 1. So a 0 at plus 3, a 0 at plus 1, and a 0 at 0. I know that because of this negative sign, the graph needs to be approaching negative infinity. So I know that because of that negative sign, that as x goes to negative infinity, y also goes to negative infinity, and as x goes to infinity, y goes to negative infinity. That's the end behavior. And I know that from this negative sign and the fact that it's a quartic. So it's a negative quartic, which gives me this end behavior. So I'm going to make the function go from negative infinity. So somewhere down here, it's got to cross at negative 1 because the multiplicity of that factor is odd. 1 is an odd number. So I'm going to be positive for a little second right here. And then it's got to go back and hit 0 at 0. But it can't cross the x-axis at 0 because the multiplicity of this 2 is even. So it's going to bounce at 0 and stay positive. And then it's going to come up and go down and cross there because this multiplicity 1 is odd. So we're going to go down again towards negative infinity, which is what the end behavior told me it would do. I don't like that because it's a little pointy looking. Let's kind of smooth it out. Polynomials are smooth, continuous functions. So it's going to go up and then like that's much better, smoother. Good. Smooth, smooth, and continuous. That looks pretty solid. Hazel says that she is confusion, which is bad. I hate it when I am confusion. Okay. So, starting again. Let's talk about just polynomial end behavior. So, in general, polynomial end behavior. Polynomial end behavior is determined entirely by the leading coefficient. So if I have a positive leading coefficient and it's odd, so let's do positive and odd. That will be as x approaches negative infinity, y approaches negative infinity. And as x approaches positive infinity, y approaches positive infinity. And that might be a graph that looked something like this. Cool. And by positive and odd, I mean that the function might be like 3x cubed. So 3 is positive, and that's an odd number. And then we could have negative and odd, which would mean that we get the reverse. As x approaches negative infinity, y approaches infinity. And as x approaches infinity, y approaches negative infinity. So we get a function that might look something like that. And by negative and odd, I mean that it might be something like negative 3x to the third, where this is negative and odd. And then we get positive and even. Let's make it a four-way chart. So come over here and say positive and even. Which would mean that as x approaches infinity, y approaches infinity. And as x approaches negative infinity, y approaches infinity. Because an even powered exponent just makes anything positive. So I'd be talking about something like that. So this could be the graph of y equals 2, or let me just make sure that this number doesn't matter. So 7x squared, where I'm saying that this is positive, positive, and that's even. And then we can have negative even, which is what we had on the test, which means that as x approaches infinity, y approaches negative infinity. And as x approaches negative infinity, y still approaches negative infinity, which would be something like that, where this is possibly the graph of y equals negative 7x squared, where that's still even, but now that's negative. Negative. Cool. So there's the four categories of polynomial end behavior. All polynomial end behavior does something like that. You can't have a polynomial that doesn't have one of those for n behaviors. So looking here, I could identify immediately that this was going to have negative, even n behavior. So I knew immediately that it had to do something like that in the big picture. It had to be going down on the left and down on the right. So the first thing I saw was negative, even, and behavior. So that meant that as x approaches negative infinity, y would approach negative infinity, and as x approached infinity, y would still be going down negative infinity. It's going to go down to the left and down to the right. Cool. Then I was asking myself, so this is the first question, n behavior. Then I was like, where will it cross the x-axis? So I asked myself about zeros. And to do that, I had to factor. So I first took negative 2x to the fourth plus 8x cubed minus 6x squared. And here I am identifying zeros when suitable factorizations are available, which is exactly what the core standard says. So I'm factoring out negative 2x squared, which leaves me with x squared minus 4x plus 3. If I were to times those all back out to the 3 terms here, I would return to this original function. And then I'm factoring that quadratic, which becomes negative 2x squared times x minus 3 times x minus 1. So this one gives me a factor at x, a factor at x equals 0 and a 0 at x equals 0. And this one gives me a factor at x equals 3. And this one gives me a factor at x equals 1. So I have a 0 at 0, a 0 at 1, and a 0 at 3. 0, 0, 1, 0, and 3, 0. And when I put that 0 on the other side when I was doing it earlier. So it's a good thing we went over it again, huh, Hazel? Okay, and now I'm remembering that I have that negative even n behavior. And that means I'm going down to the left. Like that. Good. And then I come to this first 0, which is at 0. And it has even multiplicity. Even multiplicity. Which means multiplicity. Which means that it will bounce down like that. And then I get to the next 0. And we're going to cross because this one has odd multiplicity. Odd multiplicity. Multiplicity. Because this is to the first power. To the first power. And that means we're going to cross and become positive now. And then this one is also to the first power, which is an odd number. So it has odd multiplicity. So the graph is going to come through and cross, which is good because it has to go down for forever. Like that. So Hazel, that is how I knew to graph it like that. Are you still confusion? Or do you feel better? Sweet. Good. Great questions. Glad I redid it. Number 8. We have the rational function 6 over x minus 4 plus 3. So let's see. I'm going to start by making a little xy table, because why not? X, Y, we don't need that much of an xy table. X, Y. And we're going to plug in 2 and 3 and 4 and 5 and 6. And 2 minus 4 is -2. 6 divided by -2 is -3 plus 3 is 0. 3 minus 4 is -1. 6 divided by -1 is -6 plus 3 is -3. 4 minus 4 is 0. Can't divide by 0. 5 minus 4 is 1. 6 divided by 1 is 6 plus 3 is 9. 6 minus 4 is 2. 6 divided by 2 is 3. 3 plus 3 is 6. Okay, so I've got 2 comma 0 1 2 0, 3 comma -3, 4. Looks like I need an asymptote at 4. Uh, 5 comma 9, 5 comma 9, and 6 comma 6. Okay. I am also saying I need an asymptote at 3. So this gave me an asymptote at 4. This gives me an asymptote at 3. So this is y equals 3. And this is x equals 4. And then the function will go like that. Oh, let's get the intercept correct. So what happens when we plug in 0? 0 is 0 minus 4 is -4. 6 divided by -4 is -1.5 plus 3 is 1.5. So this should be exactly there. And now we're graphing. It's going to look like that and come around. And then it's going to go towards the asymptote like that and like that. And then it's going to come from up here and head over there towards that asymptote. Great. So there's the graph of r of x, which we happen to know is congruent to the graph, the parent function, 6 over x. So if I had a duplicate, we can see that it would have looked like this function, just translated 3 down and 4 left. So that function just moved 1, 2, 3, 4 to the left, and then 1, 2, 3 down. So there's the original function, which is like a parent function of 6 over x. So this just moved me right 4, and that just moved me up 3. I feel like I should go a little more left. That's better. Ah, perfect. Cool. Any questions on number 8? Oh, wait, I haven't finished. Label the asymptotes and intercepts. I got the asymptotes, intercepts. We got an intercept at 0, 1.5, and then another one at 2, 0. State the domain and range. Domain is the set of values x such that x does not equal, we did not get the value at 4. And the range is the set of values y such that y does not equal, we never get an output of 3. There's a horizontal asymptote at 3. Cool. We have graphed a rational function and identified zeros and asymptotes. And Savian is demanding extended standards, which we can do. Any questions on number 8? Okay. Oh, I still need this, but let's give ourselves some more space for some extended standards. So I'll go over an extended standards previous test, I guess. Is that what we're thinking? Um, I think this one has some extended on it. Yeah, here we go. Good looking extended standards test. Okay, so here I'm looking at units 5 and unit 6 extended. So unless anyone has a preference on which extended standards I cover. Otherwise, I'm going to start at the beginning. Okay, so we got a file, Google Drive. More functions. Insert. And we don't need this core standards part. We do want this extended standards part. So here I'm looking at Savian says parametrics and conics. Okay, so I'll go through this and then we'll jump to unit 8 extended. Okay, so number 1 here. This is in unit 5. An extended standard was graph piecewise defined functions. And it asked me to sketch a graph of continuous piecewise defined function that has an exponential piece, a linear piece, and a polynomial piece. Okay, so here we're going to get graph, and I'm going to set it up ahead of time. I want to go in this first part, exponential. And then in this next part, it's going to be linear. And in the next piece, I'm going to do just a quadratic, I think. So I'm starting out with an exponential. And it goes up like that, and then it's linear like that. Let's go down to make space. Linear headed down, and that didn't look so good. Linear down, and then quadratic like that. Okay, and I'm gonna say, let's see, how have I scaled this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So I had 1, 2, 3, 4, 5, 6. So this is x equals 7. And this is 8, 9, 10, 11. And that's onwards from there. Cool. And I'm going to say this is 1. And my exponential portion then is going to be y equals 2 to the x. And let's see, what kind of scale did I get here? 2, 3, 4, 5. So by the time we got to 5, so when x was 7, we got to 5. So let's see, what's 2 to the 7th power? 2 to the 7th. When I plug in 7, let's get rid of all that. 2 to the 7th was 128, but I only got 5. So this is 5 128ths times 2 to the x. 5 128ths, 2 to the x. And then this next section, we go down from 5 to 1 over 4. So this section would be, has a slope of down 4 over 4. So negative 1 times x minus 11 plus 1. And this last part is quadratic, so it's y equals x minus 11 squared plus 1. Cool. So then my overall function is f of x equals the set of functions beginning with 5 128ths times 2 to the x if 0 is less than or equal to x less than or equal to 7, then negative x plus 11 plus 1. So negative x plus 12 if 7 is less than x less than or equal to 11. And then we've got x minus 11 squared plus 1 if if x is greater than 11. Cool. Can I retake a test tomorrow during lunch or after school? Hazel, I will be available tomorrow during lunch or after school. Yes. Okay. So I sketched a graph of a continuous piecewise defined function that had an exponential piece, a linear piece, and a polynomial piece, which I happen to choose quadratic. Then I wrote the piecewise definition of my function. Check. Now I'm going to find the average rate of change. So this was part A, and then part B, and I used up all my space, so part C goes over here. Part C, let's find the average rate of change. Average change on an interval that includes both the exponential and the linear piece. So well, I'm going to make it really easy myself and say from x equals 1 to x equals 11. So f of 1 equals, sorry, x equals 0 to x equals 11. F of 0 equals 1, and f of 11 also equals 1. And then I've got average rate of change of change is given by f of b minus f of a all over b minus a, which is f of 11 minus f of 0 all over 11 minus 0, which is 1 minus 1 all over 11, which equals 0. Oops. Cool. So all it's saying is that if you graphed a line here that went from there to there, that line wouldn't go up or down at all. It would just be flat from that spot to that spot. And Savian is asking, is our one page of notes front and back, I'm assuming? And the answer is your one page of notes is certainly welcome to be one page front and back. Okay, number 2 asks us to prove that the log of a to the b equals b times log of a, which is one of our standards. Extended FLE for 1. Prove simple laws of logarithms like this one. So let's see, how would I prove this? Well, I want to show that log of a to the b power is equal to b times the log of a. Um, so in general, all the proofs of logarithms mean taking a logarithm, rewriting it as an exponent, applying an exponent rule, and as soon as we apply the exponent rule, we just put it back to being a logarithm. So our first step is to let there be some number. So I need to take this a to the b part, and we're going to say, let's let a to the b be some number k. That should do it. And then if a to the b equals k, then we can Hmm. We can say that log base A of k equals b. And then if I substitute b in, okay, yeah, that'll work. Great. Sorry. So now I can say log of a to the b is the log of a. And now I'm going to take this value of b and put it here, and it becomes log base a of k, which a to the log base a of k is just k. Oh no, I didn't do anything. Sorry, everybody. How am I going to do this proof? I have to remember my proofs of logarithms. We need to justify this based on the fact that an exponent, we're multiplying exponents. Okay, so I started it right. We're going to say log of a to the b power is going to equal some number k. Okay, and then that means 10 to the k equals a to the b when I rewrite as an exponent. So I just said I've got base 10, k becomes the exponent, equals this thing, the argument of the log becomes a to the b. And then I can say, all right, let's try to get rid of this. So I'm going to raise both of these to the 1 over b power. So that means I've got, this is going to get raised to the 1 over b, and this is going to get raised to the 1 over b. So I want to move the b from being here to being over here. So this is going to be now become 10 to the k over b, and it equals just a. Which means that now when I come back to being a logarithm is log of a equals k over b, and haha, k equals b times log of a. So there it is, we showed it. If the log of a to b is equal to k, then k is equal to b times log of a. Beautiful. So therefore, log of a to b is the same as b times log of a q e d. Sweet. So we need to rewrite into an exponent, apply a rule of exponents, rewrite as a log. Bam, shown. Any questions on number 2? Okay, it's 8:25. I think I'll go for about a half hour more. Would we rather see? I think we've talked some about composition and inverses, and we've talked some about. Oh, we know this is a logistic function, which is an extended standard. But I think I'm going to try to respond to Savian's request for parametrics and conics. So let's go ahead and pull up a conics test with parametrics and polars. So pull that one up. Yeah, Savian said conics before I go. Got it. File, save as, get a PDF of it. Yes, Claudia is correct. Parametrics and conics are quarter 4 extended standards. True statement. File, Google Drive. Looking for this one. Okay, so this was on the unit 8, which was conics, which was all extended. And this was the originally intended to be extended standards for unit 8 on conics, which had polar and parametric curves. So here we have to graph a parametric curve. X of t equals 5 tan t, y of t equals 3 secant t. Find the equation of the curve in rectangular coordinates. The extended standard being demonstrate an understanding of functions and equations defined parametrically and graph them. So I'm going to make a t, x, y table, and I'm going to let t vary from 0 to pi over 2 to pi to 3 pi over 2 to 2 pi. Okay? And then when I've got 0, if t is 0, I'm going to first plug in t to my x of t function. So the tangent of 0 is 0. 5 times 0 is 0. And then secant of 0. The secant of 0 is the reciprocal of the cosine of 0. The cosine of 0 is 1. So the secant of 0 is 1. So that's 1 times 3 is 3. So when t is 0, I get 0, comma 3. So my first point here, 0, 3. 1, 2, 3. X and Y. Cool. Then when we're at pi over 2, the tangent of pi over 2 is, let's see, I'm thinking about 90 degree. So the opposite over the adjacent is 0. Is that right? The tangent of pi over 2 is the sine over the cosine. The sine of pi over 2 is 1. The cosine of pi over 2 is 0. That should be undefined. Yeah, that's no good. So I get no x value there. So I'm not going to get a y value. So let's see. What should I have let t vary from? Maybe I'll let t vary from. I'll think about the domain of the tangent function. I should get all the periodicity of the tangent function is negative pi over 2 to pi over 2. So I'll go negative pi over 2 and then negative pi over 4 and then 0 and then pi over 4 and then pi over 2. But I guess that's a bad idea because negative pi over 2 and pi over 2 are both not going to give me any values. So let's try negative 3 pi over 4 negative pi over 4. Sorry, I'm trying to show you how to do it by hand. We can just use Desmos, but it's nice to know what you're doing when you do it by hand. So we liked 0. We don't like pi over 2 because that's not within the domain of the tangent function. So let's do, yeah, I'll do my negative 3 pi over 4, then my negative pi over 2, which will be out of our domain, then negative pi over 4, then 0, then pi over 4, then pi over 2, which we won't use, and then 3 pi over 4. That'll be solid. Okay, so negative 3 pi over 4, we're going to get the tangent of negative 3 pi over 4. Let's see, what's the tangent of negative 3 pi over 4? So that's sine there is, I will definitely show you on Desmos saving as soon as I'm done with it by hand. That's going to be negative, and the cosine is also negative. So we've got a positive 1. 5 times 1 is 5. The secant of negative 3 pi over 4 is going to be the negative square root of 2. And then times 3 is negative 3 root 2. And then we didn't use negative pi over 2 because we had the domain area error for the tangent function. And then we're going to use negative pi over 4. So that's going to be negative 5. And then 3 secant of negative pi over 4 is going to be positive 3 root 2. And then 0 was 0, and 3 was 3, and then pi over 4 is going to be the tangent of pi over 4 is 1 times 5. So we're going to be at secant of pi over 4 is 1, and 1 times is 3. Is that right? Secant of, wait, no. Secant of pi over 4 is square root of 2. So 3 root 2. And then we can't use pi over 2, but we can use 3 pi over 4. And at 3 pi over 4, we get the tangent of 3 pi over 4, which is, now we're over on the left side, so negative 5. and a secant of 3 pi over 4 is negative 3 root 2. So we already got that point. And then let's use pi one last one. The tangent of pi is 0, and secant of pi is just negative 1, so negative 3. Okay, looking better. So now I've got to plot all of those points. I plotted 0, 3, 5, 1, 2, 3, 4, 5, negative 3 root 2, 1. Let's see, how much is 3 root 2 approximately? 3, yeah, it's about 4.24. So 1, 2, 3, 4, 5. 1, 2, 3, 4.24 is right there. And then negative 5, 3 root 2, 1, 2, 3, 4, 5, 1, 2, 3, 4.2 like that. And then the same on this side, 1, 2, 3, 4, 5, 2, 3, 4 point like that. And then negative 5, negative 3 root 2, so the same over there, and then there. So I've got a curve that's looking something like that, and looking something about like that, and then something about like this, and like that. Okay, so I'm clearly looking at a hyperbola, and of course, none of that by hand had to be done because this is an extended standard. You will get to use Desmos. So using Desmos is much easier. We could use that same table method, which is really smart. It like helps you really think about what you're doing. If we had sorry, a new table where we then graphed t was going to let be negative 3. Let's start with negative pi, and then negative 3 pi over 4, and then negative pi over 2, and then negative pi over 4, and then 0 pi over 4, pi over 2, 3 pi over 4, and pi. Then we can come up here and say we're going to let x of t be 5 tangent of those values. And then we're going to let y of t be 3 secant of all those values. And let's change it because I think it's a little confusing to be working like we're doing here. So this one we should recall t, and then this can change to t, and then this should be recalled t. Okay, that doesn't look like anything, but we're not interested in any of those. What we are interested in, we don't want to plot t 5 tangent of t or t 3 secant of t. We want to get the x values to be 5 I'm back. You saw me. Oh, good. Can everyone hear me? I can't see me on my end. I'm gonna refresh. Ah, there. Okay, now it looks like we're seeing me. Okay, great. Claudia can see the screen. Everyone can see the screen. Hey, hey, great news. Okay, so I just finished making the table that I had made by hand in Desmos, which was lots faster than making it by hand. It gave me all of these points, which I then graphed by coming in here and saying 5 tangent of t, 3 secant of t. So this kind of like lets you visualize what you're doing. But as soon as I get rid of this, now it'll just graph the entire function continuously rather than just a table. And we're going to do it, we said, from negative pi to pi, which will give us the entire hyperbolic function. Ta-da! Cool. Then we're supposed to find the equation of the same curve using rectangular coordinates. So we just graphed it parametrically. Now, how can we get it in rectangular coordinates? Well, we'd be looking at something like x squared over 5 squared minus y squared over 3 squared equals 1. Oh, switch. Sorry. Y first. Y squared, and the y part is 3 squared, and then x squared, and that's looking better. Cool. So this became the graph of y squared over 3 squared minus x squared over 5 squared equals 1. Cool. Any questions on number 1? Okay, number 2. I again want to make a table. And this time I'm going to make a theta r table. And I'm going to let theta vary. This time I'm going to start at 0 and then pi over 4, pi over 2, 3 pi over 4, pi. So the cosine of 0 is 1. 1 times a half is a half. 1 minus a half is a half. 3 over 1/2 is 6. Then cosine of pi over 4 is root 2 over 2. Root 2 over 2 times a half is root 2 over 4. 1 minus root 2 over 4. Oh my gosh, that's ugly now. Well, I'm just going to have to approximate. So let's see. So approximately, with pi over 4. .64. And then with pi over 2, the cosine of pi over 2 is 0. A half of 0 is 0. 1 minus 0 is 1. 3 over 1 is 3. 3 pi over 4. Let's see, the cosine of 3 pi over 4, I'm going to have to approximate again. Cosine of 3 pi over 4, we're at 2.22. Then the cosine of pi is -1. -1 times -1/2 is 1/2. 1 plus 1/2 is 1.5. 3 divided by 1.5 is 2. Cool. So that means I want to go at an angle of 0 and head out 6 units. So angle of 0 and go all the way out 6 units. So this is theta 0, r equals 6, because the theta is 0, or 6 comma 0. Then I want to head out in an angle of pi over 4 and go out 4.64 units. So angle of pi over 4 and head out 4.64 units. So that was 4.64 units out. That was r equals 4.64 because theta equaled pi over 4. Then go out an angle of pi over 2 and go 3 units to right there. So I made that spot, I made that spot, I made that spot. Then 3 pi over 4 is going out this away, and it's 2.2 units to like that. And then go out an angle of pi to that spot right there. Cool. And then the function that's made, the polar function that's made, is that one. And if I continued it around, it would, let's see, 2.22 come back to, oh, that was ugly. Come back to, where is it? It's that spot right there, right? 4, yeah. That spot, and goes back. Cool. Well, this is an ugly section. There we go. Cool. And again, rather than working by hand, we can definitely just hop on to Desmos, and Desmos can graph polar functions. So we can say, I want to see a graph of the function r equals 3 over 1 minus 1/2 cosine of theta. And there it does it. It graphs it for us. And we can even switch it into polar coordinates, and that's the graph we're looking at. So it had a vertex at 6, 0, another vertex at what would be pi 2 in polar coordinates, or 2 pi in polar coordinates, but is -2, 0 in rectangular coordinates, etc., etc. Label the vertices and covertices with their polar coordinates and rectangular coordinates. So there it is. That was in polar form. It was 6, 0. And in rectangular form, it's still 6, 0. But here we've got in polar form, again, in polar form, it's 4.64 pi over 4, and it's in rectangular form. Well, I went out an angle of pi over 4, and I wanted a radius, so I need to do that number divided by root 2. So that's going to be 3.28. 3.28. Then on this side, I've got in polar, oh shoot, I was doing blue and green, huh? 3.28, 3.28. And then, yes, Savian vertices are just the corners. So the vertices on the major axis, so the ends on the kind of the far extremes on the major axis are the vertices, and the co-vertices are the far extremes on the minor axis. So here I'm at, in polar form, an angle of pi radians and a radius of 2, so 2 comma pi. But if it was in rectangular form, that would be -2, 0. And then in polar form, down here I'm at 4.645 pi. Oh shoot, I kind of put this, I put it at kind of the wrong spot, huh? I should edit. That's not supposed to be 5 pi over 3. That's supposed to be at this spot here, 4. So it should go like that at 2.2, and then more like that, and like that. And that's 4.64, and then 7 pi over 4. And then if I was doing the same thing in rectangular form, it would be 3.28, -3.28. Cool. I could also get those rectangular coordinates by switching this function into rectangular form and saying in rectangular form, let's see, it looks like we have a center at 3, 0. So I'm thinking it looks like we have x minus 3 squared over, let's see, what's our radius? 3 squared? Plus y squared, because it's not up or down, over 3.28 squared equals 1. Oh, x minus 3. What's the length of the major axis? 3. Oh, it should be 2 and 4, huh? 2 and 4 squared. So I kind of needed that 3.28, huh? How else would you find the rectangular coordinates? Yeah, really, I think the best way of thinking about the rectangular coordinates here is that you've got your polar form, and then you're drawing this right triangle, and you know that it's a 45, 45, 90 right triangle, and that the radius here is 4.64. So then this makes this 4.64 over root 2, which is 3.28, and this is the same thing, 4.64 over root 2, which is 3.28. So yeah, you're just using your special right triangles. Okay. Any questions on number 2 from this quiz? Lindy, you get a page of notes. So if you'd like the unit circle on your page of notes, you're certainly welcome to put it on your page of notes. And then the last section, the last question on this Unit 8 extended test was on applying parametrics to a physical problem where parametric breakdown would be helpful. So it said a cannon is launched from the ground at an angle of 40 degrees and an initial velocity of 300 meters per second. If acceleration due to gravity is approximated as 10 meters per second squared, then write a parametric function for the path of the cannonball and sketch the curve it would trace. Cool. So I'm gonna sketch here a cannonball, and oh, that was a terrible cannon. Let's see, cannon looks something like that on the big wheels. They've got that, and it's shooting that way. And this angle is, yeah, they got the cool kind of thing like this and like this. That looks more like a cannon. And this angle is 40 degrees. And there's a launch vector of 300 meters per second. And we can decompose that vector into a vertical component and a horizontal component. This horizontal component is going to be given by 300 cosine of 40 degrees, and this vertical component is 300 sine of 40 degrees. And then when we write our parametric function, the x component, there's no acceleration after the initial acceleration. So we have uniform or constant velocity. So we can call that 300 cosine of 40 degrees times t if we let the initial position be 0. And then in y, there is acceleration in y because gravity is pulling it down at negative 5 meters per second every second. So negative 5t squared. But it's pushed up by the initial acceleration or the initial force that pushed upwards with 300 sine 40 degrees times t. And well, it was launched from the ground, so no starting value. So that's it. There's my parametric function and sketch the curve it would trace, and we're gonna go ahead and just use Desmos. So, oh, whoops, lots of things there. And then that, and just that. Ah, shoot. Okay, so in Desmos, pulling it up, and we're getting out of that and out of that, and back to rectangular form, and we're graphing 300. We're going to need to be in degree mode. 300 cosine of 40 degrees times t, comma, negative 5 t squared plus 300 sine of 40 degrees times t, and there it is. That's our graph, and we're probably going to need, I think I remember, like 40 seconds. There we go. Cool. So the graph looks like it goes up to like 2,000, almost 2,000 feet, 1,800 feet, and it goes, or 1,800 meters, goes almost 9,000 meters forward. So we're going to get a scale over here and say bang and bang, and we're going to go up to 2,000. So let's see, 100, 200, 400, 600, 800, 1,000, 1,200. Whoops, it should have been 200, 400, 600, 800, 1,000, 1,200, 1,400, 1,600, 1,800, and then down here needs to be like 1,000, 2,000, 4,000, 6,000, 8,000, 10,000. So the graph goes up to over 1,800 meters, like 5,000, like hereabouts, and then drops to like 9,000 thereabouts. So baba bang and baba bang. Cool. And we could do a couple things to figure out. Uh, looks like it hits the ground at maybe 38.5 seconds. 38.6. So 5, 6. That looks pretty good. So if we said, let's let x equal 38.56 over 2, and let's let time 1, and then find 300 cosine of 40 times time 1. Okay, looks like 4,000. So let's let x equal, this is x1 equals x equal x1. We get a graph there. That's going to be the high point. And let's let y1 equal negative 5t1 squared plus 300 sine 40 times t1, and y equals y1. There we get our high point, 1860, looks like. Cool. So about 4430, comma 1859. And Savian is asking, do I use questions from previous tests and quizzes and switch the numbers? And yes, Savian, probably on about 68% of the final questions, I'll just recycle previous test and quiz questions for sure. Any other questions I need to go over? So I think I did pretty good work covering quarter 3 core standards and then we did extended standards, a couple extended standards from Q3, and then we did some Q4 extended. And Lindy's asking, where did I get the negative 5t squared? That came from 1/2 of 10. So acceleration is 1/2 at squared. Acceleration due to gravity. That's the impact on the position function. So the -5, negative because gravity is pulling it down, and it's 1/2 of 10. And if we had more time, I'd be happy to say more about 1/2 at squared. Lindy, we talked about it more the first time we went over this, but probably not right now. Or you're welcome to ask. This is a great physics question. But for now, we're just going to accept that if we got acceleration due to gravity, we could write it more precisely as 9.8 meters per second squared. If we were in feet, it would be 32 feet per second squared. But when it lands when that acceleration, if we have uniform acceleration, when we see that in this position function, we're going to always see half the acceleration times time squared. So if this is 10, this will be 5. If this was 32 feet per second, this would be 16t squared. If this was 9.8 meters per second squared, which is more precise, this would be 4.9t squared. Good question, Lindy. Think, having talked now for 2 hours, I'm going to let you guys go. And I can answer more questions tomorrow. I'll see you then. Good night.